Okay. Hello, everyone. Nice to see you, at least some of you remaining. So let us recall what we discussed last time. Who will tell me what is the reason, let's say, what is the physical explanation of the second Kepler's law? We mentioned that last time. So, as a small reminder, we have gravitational force with a centric force exerted to the, let's say, planet moving about the sun. Means centric means that this gravitational force is pointed towards the center of the sun. Will such force exert any torque on the planet? No, because there is no arm level. So torque is equal to 0, means that we can apply this concept of conservation of angular momentum. So the conservation of angular momentum actually explains the second Kepler's law, which states that there is a constant area divided by the position vector per unit time. So what about the third Kepler's law? What is the reason behind it? As you may remember, we consider this stable orbit, like circular orbit, about the sun, and in that case, we have equilibrium condition between gravitational force, which is attractive force, and centrifugal force, which tries to move planet away from the circular orbit. So in that case, this originates from the second law of motion, and in order to have the stable orbit, these forces should be equal to each other. If we equate them, means gravitational force equal to mass of the planet times centripetal acceleration for this motion along axis, circular trajectory. Then we can further derive equation which tells us that indeed square of the period of this motion of the planet about the star or the sun will be proportional to the radius in cube, like in third column. So that is the reason, actually, the physical origin of this third law of motion and third Kepler's law. And further, we took into consideration statements from second law of motion, second and third Kepler's law, in order to derive or show how Newton, in his time, derived the universal gravitational law. So he was based initially on these three laws. By the way, first one was also formulated by Newton. So he used advantage also of Kepler's laws, and putting them together could able to derive the universal gravitational law, which is one of the key fundamental contributions in classical physics. So now we continue further with this analysis of gravitation, and there are several questions we still need to answer. So first of all, what is the mechanism of two bodies which possess some masses um, interact with each other. So what is the mechanism of this gravitational interaction? It is obvious that from our everyday experience, objects interact with each other when they are in contact. However, here we experience some forces exerted on these bodies, and they can be placed in vacuum, like in empty space, but still, nevertheless, there could be huge distances between this object. There is still interaction. So, and the other question which we want to highlight here during our discussion will be total mechanical energy of planetary motion. So we will consider both kinetic and potential energy of planetary motion, and we'll make some conclusions based on it. So let us first start with the interaction, the mechanism of gravitational interaction. So in order to explain it, we need to introduce so-called gravitational field. Um, every object which possesses some mass creates gravitational field around it. And if we take another object with certain mass and place it in the space where this gravitational field exists, there will be some force exerted on this body, which we placed inside gravitational field, and it will be equal to the product between mass of the body and strength of the gravitational field. So we can express gravitational force in vector form, F gravitational vector, as mass times G vector, which G vector is the strength of gravitational field. So how do you have a question? No? Okay. So how do we define this strength of gravitational field? From here, we can show that strength of gravitational field is equal to Fg vector divided by m. Um, as you remember from our first lecture on gravitation, we introduced universal gravitational law in vector form, so we know how we can express gravitational force as a vector. So what we had there, it was minus g times m, mass of the star, let's say, times mass of the planet, divided by r square, distance between these two objects, times r prime unit vector. So what it means, we have star, we have planet, here is a position vector r, which defines position of the planet with respect to the center of the star. And here is this r prime, the unit vector, which defines the orientation of position vector. Also, we should not forget about this mass here, m. So we should put it here, we cancel it out, and eventually we get for the strength of gravitational field minus g times capital M over r squared times r prime unit vector. As you see here, we do not have mass of the planet because it should not be there. So we define strength of gravitational field, which is created by the star in this point where planet is located. So then if we multiply the strength of gravitational field by mass of the planet, we get the gravitational force. Also, we have this minus here, means that gravitational field is oriented towards the center of the object which creates this gravitational field. So if we have some potential field, like gravitational field and some interaction where this gravitational force, which we know it's conservative force, we should deal also with some potential energy. So let us try to calculate what will be change of potential energy if certain object moves from initial to some final position. So let us consider again this. Here we can consider planet Earth with some radius RE, mass ME, and here will be some object with respect to with position vector R initial with respect to the center of the Earth, and then it moves to some mass M to some new position R final mass M, um, and we want to calculate the difference in potential energy between these two states. So how we define this potential energy? Change of potential energy. D delta U will be U final minus U initial. So in general form, how can we express change of potential energy? That is minus integral from initial position to final position times of the force as a function of position, and here dr. So that's a general definition of change of potential energy, equal to negative of work, mechanical work done by conservative force. So now we know what will be the force as a function of position. That is our gravitational force. So we can just write here the expression for universal gravitational law and put minus because this is attractive force. We know that this force exerted on the object is pointed towards the center of the planet, so it's attractive force. We put minus, and we can write here that this will be G times M E times M over R squared. So here we kind of care about magnitude. Now let us substitute it here in this integral and get the expression for change of the potential energy. So change in potential energy will be equal to all these terms which are in the numerator, they are constants. So masses of the planet and object don't change. G is the universal gravitational constant. So we can take it, factor it out from the integral. So it will be minus G times ME times M. And here is integral from initial to final position of what is left, and left is dr over r squared. So now we can take this integral and we will this minus actually should be plus because we have minus here and minus here. Okay. So now we have G times M E times M Then we have minus 1 over r. That's result of our integral from r initial to r final. So now we can write that change in potential energy will be minus g times m e times m, and here we have 1 over r final minus 1 over r initial. So potential energy is such a parameter which we define relatively to some position, and we can set arbitrary value of potential energy with respect to given position, and then determine potential energy with respect to this arbitrarily defined value. So we can set that let us assume that the planet or this object was located initially at Ri approaching infinity. And at that distance, we assume that initial potential energy was also was equal to 0. So if that is the case, we can consider it, and then we can write that expression for potential energy as a function of position, like distance from the center of the Earth, will be given as minus g times me times m divided by r. So this is the expression for potential energy of gravitational in gravitational field, and we will operate with this equation further. So minus here means that we deal with attractive force. The gravitational force is attractive. So now let us consider, before we proceed further, the case when we have not just two bodies which are interacting with a gravitational field, but one more, let's say 3 bodies. So in that case, when we have 3 objects, we need to take into account, and we want to determine potential energy of such a system, we will need to take into account interaction between all of these objects. So let's consider a system of 3 objects. So this will be M1, M2, and M3. And we have obviously different distances between them. So this will be R12, R23. This is R13. So now, if we want to determine total potential energy of such system in the scope of gravitational interaction, total potential energy will be equal to U12 plus U13 plus U23. That will be equal to minus G times M1 times M2 over R12 plus M1 times M3 over R13 and plus M2 times M3 over R23. So that is the way how you approach some systems of bodies which exceed just 2 bodies. So if there is 3 and more. Now, when we defined the potential energy, we can make a step further and consider total mechanical energy of planetary motion. Obviously, there will be not only potential energy, but also kinetic energy, because planet is moving along this circular trajectory or elliptic trajectory, and it possesses certain velocity vector. So it will possess both uh, kinetic and potential energy. So let us consider such a system will be ms, mass of the sun. Then we have some planet with mass m. Here is the radius vector r. This is our circular trajectory. And this is velocity vector. So what will be the total mechanical energy? E will be equal to kinetic energy plus potential. Then kinetic energy, how do we define of this planet? Oh, well, we consider the rotation about the planet, um, this planet about the sun, and in this case we consider only linear velocity vector. So we neglect with the rotation about its axis. So in this case we have just 1/2 times mv squared. So then we need to take into account potential energy. Potential energy comes with minus, that will be g times ms times m, and here we have expression for potential energy. It will be 1 over r. So we can write here like this magnitude of the radius vector. So this is the expression of total mechanical energy of this planet moving along circular trajectory around the sun. So now let us come back to previous statement when we considered stationary orbit. What conditions should be satisfied for a stationary orbit? We introduced this condition when we considered third Kepler's law. The gravitational force should be equal to centrifugal force, means mass of the planet times centripetal acceleration. So let us write this down. It will be g times ms times m over r square. That is equal to mv square divided by r. So now what we can do, let us multiply left and right side of this equation by r over 2. And let's see what we get. Will be g times ms times m over 2r, and that will be equal to mv square divided by 2. So the right side now is kinetic energy, mv squared divided by 2. And appears that we can express it in terms of mass of the star, planet, and distance between them. So now let us take this expression and substitute it here for the expression of total mechanical energy of such system. So we get E, total mechanical energy, will be equal to Gms times m over 2r minus Gms times m over r. And eventually we get minus Gms times m over 2r. So this is the expression for total mechanical energy of this system. Sound planet. So what we need to see here? First of all, it's negative, means total mechanical energy is negative. That is a sign that this is a stable configuration. Because if that would be positive or equal to zero, this would not be stable. So that's the first thing what we focus our attention. Second, if this is negative, this is stable, everything is good and doesn't change over time. So mass of the sun and planet are constant and distance between them is also constant. So in that case, the total mechanical energy is a constant parameter. It doesn't is defined by this constant components of this equation. So we can take this into account and get some benefit out of this. Because if we have some initial condition, let's say we keep in mind that total mechanical energy is a constant. So we have initial total mechanical energy, mv initial square, not plus but minus potential energy, which will be g ms m over r initial square. And then let's say something happened and um, distance between the star or the sun and the planet increased, so it changed. So in that case, we end up with 1 over 2 mv final square minus g ms m over r final square. So if we know initial and final radius and initial velocity, then we can determine what will be the final velocity for such after such transformation of the orbit. So that originates from the fact that we have constant uh, mechanical energy of the system, sun and planet. Also, what should be highlighted here that in the scope of this discussion, we assume that mass of the sun is much larger than mass of the planet. So that's important. And any suggestions why this should be taken into account? So this system, sun, planet, will rotate actually about center of mass of this system. And if this is true, then center of mass will be located very close to the center of the star. Means motion, like energy, kinetic energy of this motion of the star with respect to the center of mass of the system, it will be negligible, so we can focus only on kinetic energy of this planet. So that's why we need to set this condition. I have a question. Professor, what will happen if another sun will appear right next to the sun? I mean, two suns right next to each other. So then we will have um, system of three bodies, and if we are talking about the total potential energy, the gravitational force and that like emitter between just super close to each other, and the gravitational force is super strong over black hole or something. Well, we will mention a little bit about this concept of black hole, but there are systems like this. Sort of, as I understand, you are talking about some double star system when there are two stars located close to each other, and they are rotating about some center of mass, common center of mass. So that actually exists in the nature. By the way, this large bare constellation, which you can easily see on the sky all the time when there are no clouds, obviously. In this constellation, there is one star in the tail, which is double star. So if you use binoculars, just regular binoculars, you can see that there are actually not one, because you cannot resolve them with with your bare eyes. But if you use a regular binocular, you will see that it actually consists of two stars located very close to each other. And nothing special will happen. It's just the thing that in this system, when we have two stars, most likely this condition will not be valid because mass of star is much larger than mass of the planet. So these masses of two stars will be either equal or one will be larger, most likely one larger and another smaller, but they still will be comparable. That's why it will not be such circular trajectory. These two systems will rotate about some center of mass, so it will rotate like this. And both of them will move kind of around each other, but this position of the center where axis is going through will be defined by position of the center of mass. And it's possible that if they're very close to each other, that they start to kind of suck matter from each other and create some tails of hot plasma, which goes from one star to another. But for that, they need to be located quite close. So now, when we know this conservation of total mechanical energy, we can proceed further and determine kind of important parameter, which is so-called escape velocity. Means velocity which needs to be provided to an object in order to leave the surface of the planet and go to infinity. So leave completely the planet. Not become a satellite of the planet, but just go to the infinity. So how do we approach this? We assume that, first of all, we don't have friction, like drag force between the projectile, which we consider, and atmosphere. So there is some planet without atmosphere. And we also consider that initial velocity vector of the projectile goes perpendicular to the velocity vector of the planet, because escape velocity will be different if you launch projectile along the motion of the planet, so it will be smaller, or you launch it against the velocity of the planet. So in order to um, eliminate this factor, we consider that it's launched perpendicular to the velocity of the planet. So now we draw our planet, not very planetary. So this is the radius. Then we have some projectile on the surface. We provide some velocity to this projectile. Let's call it initial velocity. So it moves up to certain height with respect to the surface of the planet. This is h. Let's call it h maximum. So the maximum height it can reach. So let us consider what we, and this is capital M is the uh, mass of the planet, small m is mass of the projectile. Let's consider what do we have initially, what total energy of this projectile will be at initial moment when this velocity is provided. So it will be sum of kinetic and potential energies. Will be 1 over 2 m small m times v initial square plus, actually not plus but minus because we have negative potential energy, g times me times m. Well, me is we consider planet Earth. So let's consider planet Earth. Me times m divided by re. So that is total mechanical energy of the projectile on the surface of the planet when it receives this velocity vi. What do we have at the maximum height? There will be some kinetic energy. Obviously not, because we don't need this. Well, we don't get any kinetic energy remaining, since it will be completely converted to potential energy, because that's the definition that it can reach some maximum height. It cannot go further because all kinetic energy is gone. So in this case, we will have only potential energy that will be equal to minus g times me times m over, and here we have um, r maximum, and this r maximum can be expressed as re plus h maximum. So means we have this radius re plus this h maximum. So that will be the distance between the projectile where it reaches maximum point to the center of the planet. So from here we can express already initial velocity. So we can also cancel out this mass of the projectile. It doesn't matter which mass it possesses. And now velocity, initial velocity square, will be equal to 2g times me times 1 over re minus 1 over r maximum. And instead of 1 over r maximum, we can substitute its expression here. So it will be 2g times me times 1 over re minus 1 over re plus h maximum. So this is the expression for vi squared. And what we want to consider here, we want to determine escape velocity, means velocity at which the projectile will leave the planet. So what condition we should set here? Which parameter will define where this projectile will end up with respect to the surface of the planet? H max. So if we assume that it goes completely away from the surface, H max we approach to infinity. Then this term with H max in the denominator will approach to zero. So if H max approaches to infinity, then this will be zero. So what we can write now, that V escape will be equal to square root of 2g times me divided by re. So that is the escape velocity when we do not take into account drag force, interaction with the atmosphere, and also we assume that the provided velocity vector for projectile is perpendicular to the velocity vector of the planet. So if we substitute here expressions for like magnitudes for mass of the uh, Earth and radius of the Earth, we will get escape velocity something about 11.2 kilometers per second. If we do this for Moon, for example, that will be something about 2 kilometers per second. If we consider Jupiter, then it will be enormous 60 kilometers per second, taking into account that Jupiter is the largest planet in our um, solar system. So obviously that the with increase of like change of these parameters, mass and radius, we will have different escape velocities for different systems and different planets. However, the most interesting is when we consider stars. So, to be more specific, when we consider stars in their evolution. So, what happens with stars? If a star possesses mass which is smaller than 1.4 mass of our star, which we call the sun, then most likely it will evolve in a white dwarf. So it will not have a chance to get more compact and go to neutron star. But if mass is larger than 1.4, then there is a chance that there will be after white dwarf, it will cool down and constrict. So density will increase, it will convert to a neutron star. And if mass of the star was much larger than 1.4, it's something like more than 3 masses of the sun. Then there's a chance to reach enormously high density, and there will be very small object. Neutron star is a very small object with enormously high mass because its density is close to the density of the nuclei of atom. So what we have here, that mass is huge, but radius is very small. And then this escape velocity will be enormously high. So at some point, it gets so high that escape velocity becomes larger than speed of light. And speed of light is fundamental feature of the universe. Nothing can move and travel in space faster than light. Photons, which are considered quants of light energy. So that means at certain point, this object can become of such high mass and small radius that at a certain distance around this object, there will be condition when escape velocity will become larger than speed of light. And the sphere, which like encircles this object, for which uh, this condition is true, that escape velocity is larger than speed of light, will be called event horizon of this black hole. And by definition, black hole means that it does not reflect any, like does not emit any light. And that happens because when photons come too close, like beyond this sphere defined by the event horizon, the escape velocity is larger than speed of light. So if even photon not fast enough to escape such object, its gravitational field, then nothing else can escape because photon is moving with the highest possible speed in the universe. So that means we end up with a black hole which only can absorb light and matter, but nothing goes out just because in terms of this escape velocity, if we consider escape velocity will be larger than speed of light. Nothing can move with higher speed, means there is a limit of kinetic energy which you can provide to an object is limited by the speed of light because you cannot exceed this velocity, and that's not enough to escape this gravitational field. So we end up with a black hole. Yes.
Isn't there are ways to travel faster than speed of light? So now, like,
Well, there are series of traveling in different dimensions, but if we consider our uh, universes like 3 dimensions plus time, uh, so far we don't have any mechanism to exceed this speed. So that is the highest speed of uh, potential motion, and what we can take an advantage of it, we can transmit some information like electromagnetic waves. They travel with speed of light. So that is the way how we can communicate, and that actually limits us because if even we have some rovers on the surface of Mars, there is a delay between the moment you send the command to this rover, will be something like 11 minutes, and then you need to get response from this computer and which controls the rover. It will take another 11 minutes or plus minus because it depends. It's not always constant distance between Earth and Mars. So it will be like over 20 minutes to send command and get feedback. And that could be quite a challenging task because imagine you need to drive a car which will respond to your command only in 10 minutes, and then you will see where actually it goes with another 10 minutes. So it's quite a challenging task. But again, it's limit of physical possibility to transfer any signals with speed of light. It would be good if we can send our electromagnetic waves with higher speed. So then it would be like correlated with uh, each other quite well. We would be able to control the systems much easier, but that's impossible. So we are limited to this speed of light, which is about 300,000 kilometers per second.
Professor,
Yes.
I mean, I was thinking about the big spaceship just bending the canvas of space behind us away and traveling much faster. It's like a
Well, again, so there are theories, but technically this is not achievable at current stage. So we stick to this fundamental feature of our universe that All signals matter and travel only with speed of light.
What about teleportation? I think we succeeded there.
That is another great theory, but again, we don't handle such technology. Yeah, unfortunately. Yes?
I thought that near event horizon, time flows relatively slower as if it stays still. It stops.
Sure, that is general relativity. And indeed, when objects are moving with speed of close to speed of light, like comparable, then time flow is different as it would be at normal velocities which we experience. And that's something which quite well explained and is used in, let's say, design of accelerators of different particles. So there are accelerators where particles are accelerated with electric field to very high speed, which is comparable to the speed of light. Smaller, cannot go faster, but comparable to speed of light. So then you need to deal with relativistic principles, relativistic mechanics. Otherwise, you cannot describe the behavior and trajectories of these particles. However, in everyday life experience, this classical mechanics, which is described by Newton's mechanics, let's call it like this, at which we study in the scope of this particular course, is enough to get very accurate results. So actually, universal gravitational law is applicable to calculate orbits of satellites which we as humankind send to external parts of our solar system on such huge scale and quite high velocities, but they still are much, much smaller than speed of light. So we still can operate with these classical mechanics principles, and we will get quite good results without need to go to relativistic mechanics. But for accelerators of elementary particles, then when velocities are approaching to the speed of light, there we cannot apply Newton's mechanics. So with this, we finish our discussion of gravitation. Thank you very much for your attention. Hope you will have a great fall break. We'll rest and have full energy to come back and finish the semester with great grades and good mood. Okay, see you in a week.